From a managerial perspective, from a corporate perspective, you'll have a group of people that would be interested in whether the mine site actually understands the different risks that's involved with the plan, and whether that can be minimized. And geotechnical risk will ultimately form one of those. From Jay's perspective, legal perspective, government organizations, their interest would be about whether the company actually understands all the geotechnical complexities, and that they are adequately considered in the design going forward. Now, ultimately, the shareholder and the investor, they're interested in creating wealth with a minimal risk. They want to turn around those imaginary little numbers and get their bank accounts nice and fat. The key thing to remember is that for them, the underlying technical challenges are of little interest. They're really not interested in that. They will be more knowledgeable about what risk is, and risk is a number, and that's usually a way that we need to be able to demonstrate to them that there is a due process that's being followed to manage the uncertainties and the risks associated. Now, what we have here is a couple of examples of ground control and inundation hazards and risks, as we can see. Unfortunately, when we think about geotechnical engineering, the key is that these big impacts are the ones that's foremost on mind of people. And it is because that they have quite major to extreme impacts on the business. From a safety perspective, very possible to have multiple fatalities. And from an economic perspective, you've got to think about the fact that you may not achieve the life of mine plan. You can ultimately defer or sterilize several reserves, or in extreme cases, it can result in a force majeure. And as such, what you should have is these type of risks, geotechnical related risks, should be at least on the top 3 of any mining company's risk registers. Another thing to keep in mind is this is the type of stuff that's in the back of the investor's mind, and whether they may ultimately have a extreme impact or not. It is these events that ultimately result in financial losses, and that's because of uncertainty. If we do not understand what they are, we can't identify them, we can't manage them properly. So when we look at managing geotechnical uncertainty, it's important that we require an understanding of what drives the potential failure mechanisms for a specific design, and what can be considered realistic amelioration options for that design going forward. So your level of confidence in the knowledge that you have about the rock mass is very, very important. In previous presentations, we looked at areas where you see a number of drill holes. Obviously, you don't have drill holes all over. You need to start inferring some of the information. And as been highlighted, you can only infer so far before you've got to understand that's a very, very, very wild guess that you have. And you need to understand what the limitations are in terms of your knowledge. For me, the ultimate key is that you need to understand how that rock mass will react when we start mining. There's a loading conditions that we start imposing on the rock mass itself, and those conditions will result in how the rock mass will behave and how we can actually treat the rock mass so that it doesn't cause any problems for us going forward. One area that you would have seen a previous colleague of us, Joe Siri, work on quite a lot. He's doing that in his private time now as well with his own little Bastion company. Is looking at the reliability of the data that's available and the assumptions that needs to be made because of the limited information or because of the information that you actually have available. That's a foundation of all our decisions going forward. When we look at the methods that we use to assess and to evaluate our information that we have available, You have people that very, very quickly will dive into wanting to get numerical models set up and run them without really understanding what exactly it is that they need to evaluate for that specific mining sequence per se. Ultimately, it's about providing apt design guidance to the mine planners. Okay? And design guidance isn't just limited to a number of geometric parameters. There's much more detail to it that you need to be able to add as well. The key thing there is that you can't work in silos. It needs to be an integral part of the whole process. So geotechnical engineering and the mine planners and the production people, the geologists, everybody needs to be talking together the whole time. If we want to be able to be in any position to properly manage the different levels of geotechnical uncertainty. So gambling is a good way to explain it. What would you like to have if you understand that you know about one thing and there's a whole lot of others that you don't know? It's a toss of a coin. But if you can actually start identifying what each and every one of those potential uncertainty areas are, what they are, and be able to describe it, actually get you a little bit more of these Dungeons and Dragons type of dice. That unknown that you don't know about is much less likely to occur. So it's important that we understand ultimately what all the geotechnical uncertainties are, and that we can thereby adequately manage it in the geotechnical design. Now, any well-founded mine design, we've got to understand that is reliant on a specific level of geotechnical effort that has been put in, that's appropriate for the level of design. And we do that to provide assurance that that specific mine plan can actually be achieved. Now, in this little breakdown, there's 9 different input areas that we've identified that we need to adhere to in order to demonstrate that sufficient geotechnical work has in fact been done to manage the different geotechnical risks through the process of geotechnical design as is. Now, when we look at mines in the operational phase, obviously the level of confidence that you have to have at the operational phase is going to be much higher than for mines that's say, for instance, on a feasibility or a pre-feasibility level. But for argument's sake, let's say that there is a mine that is operational, and you go through the review and you see that, okay, maybe the geological model is up to spec, the structural model is up to spec, but not that really good about the rock mass fabric. It's important that there's some plan that's actually put in place to be able to identify where you are lacking, gap analysis, perform a gap analysis, and use that to define the work program that you need to put in place to make sure that you can get up to the required level as is. Now, in AngloGold, we've got a number of principal geotechnical engineers. My apologies, it's about the only faces that you'll see today, present, past, future. And those principal geotechnical engineers provide regional sign-off in terms of the geotechnical designs that we do. And we go through an annual review of all the different ore bodies on all the different mines to make sure that we actually know where we are in terms of the mine plan, and that we have a proper gap analysis completed to make sure that there's a work program to be put in place going forward. Now, that's the broader sort of picture. Now, you obviously want to know what exactly are the little different sort of detail levels in each one of those areas, input areas. Some of you might be familiar with this table. Now, don't worry about reading it. It's just the table that has been put out in the guidelines for large open pit design. And this has largely formed the basis for the table that we use to populate what the requirements would be for each project phase on each one of the data requirement areas going forward. We've expanded that a little bit to cater for the different impact levels. Well, we realize there's a number of mines where they might go into a specific area. They might mine a satellite pit or something like that. That satellite pit doesn't really have much of an impact, and trying to impose the same level of geotechnical requirements that you would for a $5 billion project it just doesn't make sense. So we've broken it down into the potential impact, the financial impact in terms of a low, medium, and a high scenario, and that guides through conceptual pre-feasibility, feasibility, all the way through to operations for each one of these categories. What we consider to be the minimum requirements for a specific geotechnical design, the input to a geotechnical design going forward. So, if you look at the typical completed geotechnical design, we need to make sure that the engineer can communicate the risks and the various specifications, parameters, the different options pertaining to those parameters. And of course, as I mentioned earlier, it's not just about those geometric items, it's about the operational considerations for the specific plan. Open pit, the plan doesn't change that much, but underground, the plan changes almost on a monthly basis. I'm pretty sure that over the last month, especially in gold mining companies, as the gold prices has soared, those plans would have been changing on a weekly basis. So we need to be able to provide a detailed description of the geotechnical risks in the plan, where they occur, when they occur in the schedule, and what exactly happens. It's all good and well to say you've got a risk there, but you've got to explain to the people what exactly that risk will entail, what we'll realize when that risks happen. The mining geometry parameters, so knowing what every dimension and angle or shape would be for that specific plan that you're going to be putting in place is very, very important. There are certain parameters that is chosen by the mine planner, preferred parameters in terms of what the equipment capability may be. But ultimately, those parameters, say for a bench height, if they can draw 20 meters, that parameter will impact on the bench face angle or your catch bench. Same with the stopes. If there's an interlevel spacing of 25 meters, all that will ultimately impact. So whether they choose it or not, it is a geotechnical parameter going forward. Sequencing specifications in terms of this, when and where a certain extraction will take place. Again, typically sequencing is much more prevalent in the underground mining scenario. What is usually the case is that the best sequence for the mine planner is exactly the opposite for what's best from the geotechnical perspective. But it's important to take that into account as well. The risk amelioration specifications in terms of the ground support, in terms of the monitoring that you do, in terms of the data collection that you need to do, it's extremely important. We can't just sit with the feasibility level design and expect that to keep on going ad infinitum. That needs to be updated. Think about it the same way that you may have a resource model. The geologist will still go and do ground truthing of that model with a grade control. Same work that we need to do in terms of the face mapping and observations for how the rock mass is behaving. Tolerances and options. What do? We just give one number. Boom. You can do it 20 meters. Leave it at that. Can't do that anymore. It's about really refining what every and each little stope can do. Can you actually go over 1 meter? If you can go over 1 meter, fine. If you can go over 3 meters, maybe there's an opportunity to push that. But you've got to be able to hammer down that if you mine this specific stope number A, or stope A, you cannot afford any mistake, because the impact for that stope may be significant more than what you would have for another stope where you can mine 5 meters more. It wouldn't make that much of a difference. So it's important to understand what the tolerances are, not just in the rock mass, not just in your support, not just in the monitoring equipment that you use, but in terms of how the total holistic view happens for that specific mining area. And then, of course, what's the options that you have? It's all about optionality. Operational considerations we've spoken about already. We tend to provide, let's say for instance in an open pit scenario, you tell the mine planner that your inter-ramp angle is say 55 degrees, your bench face angles is 85 degrees, your bends need to be 12 meters wide because you're mining 20 meter high benches. And then they go and they do not buy a pre-split rig, or they do not buy sufficient cleaning equipment. Or one of my favorite cases was actually at Potties, where the bench was about 20 meters high. They bought a scaler with a 30 meter boom in the plan. Some accountant decided that the benches are 20 meters high, so we can reduce the cost of the scaler. Let's just buy one with a 20 meter boom. Okay. 20 meter benches, 20 meter boom, it makes sense. No, it doesn't. So those operational considerations on how you spell it out and communicate it is extremely important. Remember again, it's about the geotechnical design and how we communicate those modifying factors and how that eventually feeds in, directly, indirectly, whether you know it or not, that goes into that final report that is being released to public. So if you go to your company's website, get the annual report, wherever there's a reserve declared, your input is there. So just to end, you would have seen some of the nice little colorful pictures that Kobus has shown with France. The whole geotechnical block model scenario is extremely important for communicating geotechnical information, whether it's information such as in this specific scenario, looking at extraction ratio and highlighting the areas in red where the extraction ratio is much lower. It helps people focus on where the problem areas are, get to understand why there may be problematic areas. So what you have as highlighted on the slide, you can see there's areas with lower rock mass, this area where the ore body is much thicker, or where the dip of the ore body is changing. All those contribute to the extraction ratio ultimately. Brocky, apologies, I should actually put down there on the little thing there. This is a Brockman design. Yeah, if you don't know, Brock is the first person that I knew that could actually get extraction ratio onto a geotechnical block model. What that does is it facilitates communication. Us talking about a number, Q number, whatever the tensile strength of some support unit is, it means nothing to the rest of the guys. They go blank. They don't know about it. But when you start talking dollars, actually physically pointing where stuff is happening, you get much more of a communication going. Did I break it? I'll just... It's not touch screen, eh? Yeah, flipping man hands and breaking it. Sorry, Fred. Fred's hand nearly cracked today when we shook it. Let me just quickly use the manual thing. There we go. So you would have seen what Kobus spoke about earlier. Here's just a simple way that you ultimately want to get to, because we're talking about reserves, remember? There's geotechnical modifying factors that goes in, and we want to be able to show where in a specific extraction sequence for a specific area where the high risk, medium risk, and low risk ounces are. So this is an example of one of the mines that we had where the initial plan, oh goodness, what did I do? What's the left and right buttons for then? Left and right, okay. Okay, I'm going backwards now, so anyway, let's not digress. There we go. Now it works. I think somebody did hack your computer. So, little red button, there we go. So what we have here is an extraction sequence from the mine planner using some geotechnical input. And you can see that there's obviously a number of ounces in the medium risk, a couple of low risk ounces, and then the high risk areas. Another sequence that gets assessed, and you can see what the breakdown is if you require ounces. I think the battery might be going flat there. If you require ounces, you want to break that down into the low, medium, high risk area. So very, very subtly you can see where different stopes might change between these two areas. The key thing is, in this specific scenario, the guys needed to have more ounces from that specific ore body. Now we can make an informed decision to see that yes, you can get more ounces, but there's a change in the little bit of a risk profile that you need to consider. You also know where those stopes are. Now you can make decisions on what you need to do to manage the risk in those specific areas. So just in conclusion, it's important that we as a geotechnical engineering fraternity can have discussions with mine planners, with management, with the decision makers on what the different risks are. Now over the years in mining, what I've seen is that there's been more loss of opportunity that has happened because of the lack of geotechnical input than these extreme events that would have happened. Some of the miners can sort of manage it. That one slide, they know how long they can drive the trucks. They'll tell you they know how long they can drive the trucks over that crack in the pit wall before they have to pull it back. I mean, there's nothing more knowledgeable than a production engineer. But I guess we just need to keep in mind that we are in fact altering nature, okay? And nature's got no interest in whether our budgets or schedules or plans are being kept, okay? It's only interested in re-establishing that equilibrium that we have disturbed. As such, we got to always remember there's certain limits that sometimes we just cannot physically exceed. But we need to have a detailed understanding of everything to be able to make those decisions and to understand what it is. Well, thanks, guys. Any questions?
Thank you, Emrich. I think definitely Anglo got a chance to tackling to track what you were saying, especially after the production engineering comment. So yeah, thanks, Emrich.
Just a quick question there. Just for my purpose, just understanding the risk again, trying to get my head around what are we trying to communicate. If we're saying that we're sitting in the high risk category, does that mean that we're at risk of actually not retrieving such ounces, or is that just at risk of diluting it too much and thus higher cost, but you're still getting your ounces? What's your definition of those risk categories?
It can be both. Okay. I mean, it depends from stope to stope. So let's say these chairs are different stopes that we have to sort of mine. Now, if I start a sequence from the furthest one coming into this direction, and say for instance I've got a fault that's sort of dipping up, right? Obviously, depending on which way you mine, somewhere along the line that fault might initiate and eventually start causing dilution. So if I come from this side, maybe the scenario is such that I can take that, and eventually I only run the risk of exposing the fault when I get to the last stope. And hence I've mined all this, and ultimately that's the low risk scenario. But that stope is the one that's at risk. But the mine planners only have an access from this side, so they want to start from that side. So now you've got to say, well, what do I know about that specific scenario? If I mine that fault, let's start mining it, understand that it's there, have it in the schedule that when stuff goes wrong and I need to re-establish, i.e. leave a pillar or whatever, lose out on this slightly lower grade area here, but I can still go mine there where Michael sits. Therefore, I know what the scenario is. There's a high risk there now, but I can plan around it. So it's not just about the loss of stope there, it's about understanding what can go wrong, preempting it in the plan, and make decisions on how to go. You can't just blindly go in, because currently what would happen is, there's the stope sequence, the geotechnical engineer, some 2-year out of university, I'm going to listen to him, I'm going to start here and I'm going to mine. When that rock falls, or bounces off the thing, if there's a rock, swell, water involved, it's a geotechnical engineering problem. Write it up, lost because of that. It's not. There's more to it in how we do that total extraction and to plan. But that's extra work. Who want to do that? I've only got one plan in place. Leave it with that. It comes to the point where there's got to be more. We're getting more and more into the area where you can't just have one plan. You've got to have multiple plans, and you've got to understand what do I push here when I do that specific scenario. Of course, I get the ore out quicker. I lose a low grade area maybe. But instead of coming around, redeveloping, there's a cost, there's time. What's my trade-off?
Risk mitigation.
In terms of, yeah.
So you've got to just quantify it for your own purposes, essentially.
And that's why it's so sensitive for the plan. It's got to be about relooking. As Kobus has mentioned, is if you're working on the mine, you know exactly what the things are. You know, when you look at the mine plan and you say, oh, that's going to go pear-shaped. It's like a typical guy after a long barbecue, whatever. Engineers are not the most articulate people. We talk in numbers and stuff like that. So to explain it and to try and use words to convey a message to somebody that doesn't even understand it is difficult. I mean, we've got problems communicating between us, even though we understand what's going on. But now imagine trying to communicate to somebody else. Get it into high risk. There's a gentleman in the audience here who says that the color red is amazing. It's amazing what you can do with the color red. Just paint it that color, and you have people's attention.
All right. Any more questions there? Rob? Quick one, bit of a kind of comment question. You obviously work for an advanced organisation who's got a good handle on, a good understanding of geotech, hazards and risks, and the organisation obviously does things the right way. There's another end to the market in which we all work, where you've got a junior who wants to get a resource out there and push the share price up, and they might get the geologist to make that an indicated resource.
Hence that 3-stage story.
So that they can then, potentially get that converted to a reserve. To do that, they need a mining engineer to sign off, not a geotech, but they do a geotech to ideally get that level of confidence to the PFS level, is what most people would say for reserve conversion. In my experience, you've got the client who's just pushing things to get it ticked off, and in my experience, the mining engineer, the geotech isn't always one of their most important things, so they'll probably be more concerned with the geology, which is something that signs off on, and then with potentially the metallurgy and processing. But when they come to the geotech, they can be quite happy if that's not at PFS level, they'll just carry on anyway. So is that anyone else's experience, and how do you deal with that as an industry? Because we can try and convey messages to them as best we can. They probably won't read our report, they'll just read the exec summary and look at the table they put in their whistle ball. But it doesn't seem to me like the mining industry and the mining engineers doing the mine planning consider geotech to be as important in order to sign off as geotech might.
Yeah. So there's two components with that public report. It's about the resource and it's about the reserve. In each one of those, there's appointed competent persons that needs to sign off. So usually the resource will be a geologist, and they need to follow a process that can be externally reviewed by potential investors, etc. I mean, Poseidon is one, Brex was another one, where, if you remember the guy, helicopters and things like that was the myth. it's important that competent person provides a sign off on that, and it's a legal appointment. Okay, so for you to change, whether it be in Australia, or London, in New York, or in Johannesburg, each country and their stock exchanges has certain codes. You've got JORC here, you've got Summeric, you've got that weird number business in Canada. There's requirements that you need to be able to go through, and they stipulate the requirements. And I guess if we're going to go around the room and say how many people has read the latest ground control code of practice, I saw the front cover, it's nice. The same applies to I suppose the competent people signing off, is that they may not be 100% familiar with what the requirements are in those specific areas. So then the resource is signed off, and that's why the mine planning engineer will be interested in that, because that's where the money comes from. It's the resource. That's where my focus is. It's a day-to-day activity that needs to be done in terms of understanding where the grade is, mining it, and getting it through the plant. The geotechnical things is a little bit too airy-fairy and long-term for them. And that's why you've got to get people coming in, and hence the design parameters. So that conversion from resource to reserve is the second competent person that comes in for that declaration of reserves. And that's usually a mine planning engineer, because of all the modifying factors that they need to apply on the resource model, okay, and to be able to say that is ultimately the reserve going forward. Again, there's a whole bunch of requirements for them to be able to do. So it's like Jay said earlier, is you're driving home in your car, whether the speed limits are there and everything like that, whether you do it or not, nobody's there to enforce it the whole time, but the one day that you do decide to go 60 in a school zone, there will be a guy with a camera that sits there and says, well, sorry sir, you drove too fast. Here's a little fine. And that fine is something that can be imposed ultimately. The competent persons will be members of certain associations, so Oz IMM as a registration for competent persons, and if they are found to lie or to not accurately represent the information, they can lose that registration, and they can effectively lose the ability to practice as a competent person. It's not stuff that sort of, I'm pretty sure if you're going to go into any flipping big company and you say, well, who's the competent person? Me. You're going to find one guy that's not familiar with what the heck it is that they need to do. They just know that I got to do the resource model, or I got to do the reserve model, and that's it. Whatever the other stuff that's coming in is don't know what that means. But when you start looking at these juniors, I think what you'll ultimately find is that the geotechnical recommendations that will be given, inherently that geotechnical engineer will take into account that they are dealing with a junior, they're dealing with less information, and that design, I can guarantee you, will be much more conservative than what it ultimately would be. So I can't deal with them, I can only deal with the guys in here. And that's easy for me, because I send Julian chasing into the guys with the open pit, and I send Kobus chasing into the guys with the underground. You've seen the size of their hands, I'm scared.
All right, now I think we've got possibly time for one more question while Julian loads his presentation, but is there anyone else? No, thank you very much, Emrich.
All right, man. Yeah, don't break it.
While Emrich's taking out, when I was studying civil engineering, one of our lecturers was also running a consulting company, and he told me that every consultant will have a list of modifying factors, so you apply your partial safety factors. And they'll have a special custom list depending on who the construction contractor is. And I think, you've got that secret list, you just got to admit it.
All right.
Yeah, can you believe it?
Big company. So, yeah. They don't even know who their colleagues are. Now, over to Julian for some more open pit related and continued story. Thank you.
Here we go. There's the mouse. Right, well, good morning, everyone. Before I start, I just want to give you a couple of warnings. So, just listening by the questions that my colleagues got earlier this morning, I just want to remind us that engineering is about making good decisions. It's not about predicting the future. And that's one of the main differences between a lot of science and engineers. Right? A lot of scientists focus their time on being super precise. And in the process, they're super expensive, they take super long, and ultimately no useful decisions are made based on what they say. Whereas engineers aren't that lucky. We actually have to produce information that is useful. And to be useful, it needs to be approximately right, not precisely wrong. And it needs to be on time. So yes, for the question about, yes, the block model isn't precise enough and it doesn't quantify exactly the right distance to the borehole. That's super right, yes. But I'm not going to spend 4 weeks to produce an answer that I need tomorrow. Whereas an approximate answer is far more useful. So we'll lead you into that. The other warning is Quibus. He's done a lot of work on schedule integration and mine risk and so on. And 2 weeks ago, he told me, "Why don't you do this for open pit?" And I said, "Well, I know I've been doing lots of risk and I've got all these fancy ideas, but he challenged me to get it right." And I actually worked out a way, and it's not perfect. You're the first people to see it. Emrich hasn't even seen it yet. If you like it, it's because I rose to the challenge, and if you don't like it, Quibus, it's your fault.
Let's have lunch now.
So just for today, I've broken it into the slope performance index. Now you'll notice this is a trigger warning. For those of you who don't like Tim Sullivan's paper from 2013, please go have a coffee now. This is going to trigger you. At the same time, I'm not here to discuss the merits or lack of merits of his paper. I'm completely neutral. I just thought it was a very interesting way of looking at things. And for the purpose of the presentation, it seemed to be quite useful. I'll probably modify it a bit going forward. The second thing is I'll show you just how to add the risk to we call it the geotechnical model for rapid integration, but it's just a block model. Except if I call it a block model, because it doesn't have volumes associated, then I get in trouble. So we gave it a fancy name, and now it's our IP. And then I'll also show you how to integrate that with the GMRI. And essentially doing the same what Quibus did, except for open pits. So going back to the GSPI, or the Global Slope Performance Index, whether you should use this for slope design or not, that's a choice you could make. But essentially what Tim Sullivan said is, looking at slopes, there are several risk factors, and he picked on 5 of them, right? And it's very clear to us. If the first one is strength, and he publishes a couple of strength ratings, and then he gives it a GSPI score. See if that works, right? And we can all agree that in general, hard rock is better than weak rock. So the way that the score works is it's 5 factors. Each one of them gets a score out of 5. You add all the scores together, and the higher scores are worse than lower scores. Very simple. Right? And so we can all agree that generally speaking, what's happening here? A strong rock is better than weak rock, so we're going to score weak rock higher on the score than strong rock. Nowhere in this indicator that does slope height or angle come in. And I know this was one of the big criticisms that he got when he published the paper. People, was very upset afterwards. But that be as it may. His answer was that he said that he assumes that the slope is already designed. So this is not a design tool. This is just a performance indicator afterwards, and it's got some interesting results. Right. So the second score is you would have seen this figure. We all know and love this figure from Hook on the GSI, and he's just given some extra prescriptors, and he essentially scores it, again, 1 to 5. It's very coarse. Again, we can agree that better rock is better than worse rock, and so we add the score up. And this is an interesting one, and if if you're struggling to get to grips with rock mass ratings and you're new in the business, read his paper. If you get nothing else out of it than the description of why this is something worth looking at, I think you've learned something, right? There's a lot of the older rock mass papers that try and communicate this concept, but I think Tim's got a nice way of explaining it. So just look at that. And essentially, this is sort of a broad diagram with all the possible geological features, and he just gives you a score again from 1 to 5. So just for example, one massive rock, if you're in massive rock, you're probably going to have better performance than where's a 5, than if you've got these predefined sheeting joints or so on. So obviously, there's some value in this. And then this is quite a difficult one. So we've got this orientation with respect to the slope that needs to be incorporated. So immediately, this GSPI is not just a function of the rock. You can't say, this is a rock with a GSPI of 20. No. With respect to the slope, the GSPI is 20, right? It takes a bit of time to figure this out. This is probably, if you're going to use the GSPI in a block model sense, this is probably the most difficult bit to program in, because you need an if statement. If the slope does this and the bearing does that, this is really the most difficult equation. And for those of you who use Peter Lilly's blastability index, there's a very similar rating that deals with this. And I often wonder if you can't correlate the two, or possibly get rid of the one and use the other one. But again, score from 1 to 5, good to bad, as a contributing factor. This is another interesting one. So we all know, if you look at Biniavsky's rock mass rating, there's a score for water. If you look at Laubscher's rock mass rating, they've got all these descriptors. Q's got some water descriptors, and that's all fine. But in terms of slopes, really, we're looking at effective stress. We know this, right? And I just thought it's interesting that these descriptors are actually based on the water level in the slope. So, and you can equate this to RU values for those of you using RU values, right? But again, no water is better than lots of water, and there's your score. So he's essentially scoring the contributing factors to risk. And then finally, you add them all up, you'll get a score between 5 and 25. 5 is fantastic, 25 is really bad. He says in the paper that he's got a database, I think it's 130 slopes, and he's correlated that. I would have loved to see the database. Being in mining, I suppose he wasn't allowed to share that information. But essentially he says that if you use his strength classification, or the PSM classification, generally, from what's it, practically you'll get 5 to 22. These are the type of failures that this is your performance classification. And there's another table in the figure that we don't need here, but in the paper. If you go to the paper, you actually correlate the scores to the scale of failures that you might get. So at the lower end, you might have rockfall, and then you get barrier failures, and then you get interramp, and look, without the database, I'm not sure if you can really use it like that. It's probably better to do a mechanism-specific analysis. But in general, that's good, that's bad, and if you want to risk assess your schedule, this is one way of doing it. Now I'd probably take Cobus's approach and say, well, what's important for your mine, right? I use this for illustration purposes, and I'm starting to look at it. But if you realize that for your mine, a particular combination of factors becomes really important, then build that in. Forget about about this. The take home for this presentation isn't to use Sullivan's rating, but rather the idea that you can populate a block model with your risk, and that it can be useful. So for this example, I can't tell you where this is. Cal, I'm sure you'll recognize it. Just to show you the geology, this is a pit design. You've got the two most important rock types, ANF, ANG. You've got some shears, which are the blue. I haven't put all the shears on here because the other ones are also joint sympathetic, so they're just taken care of as anisotropy in the model. And then you get a dike. Now immediately, if you produce this figure alone and you say to a guy, don't mind this pit, there's something useful in here, right? I mean, you can expect to have some issues with the dike. This is the footwall. It doesn't show up on this figure, but the site geotech will immediately tell you footwall will give us issues. Just look at what we're getting. And it's saprolite, and the same thing. We know that there's going to be some issues that deal with saprolite. So I can tell this to the geotech engineer on site, and he'll understand what I'm saying. But if I take this to the manager or the regional manager of mining, these words mean nothing to him. So how about we populate the individual scores for the GSPI index or some other index. It doesn't matter which one you use as long as it's relevant for you. Imprint that on the pit shell, and that's very easy to do in Gem4D, right? And you calculate the GSPI, and in this case, I've actually managed to put the two major joint sets into the rating as well. So what I've done for this one is the rating that looks at the orientation of structures with respect to the slope. I've just picked the worst one. So I calculate that for the two major joint sets, and then for the GSPI, I picked the worst one to try and get the idea. So it's not a proper kinematic analysis, but it's not irrelevant either, right? And what you then get, according to his rating, so the blue areas are generally stable, and that's actually our experience. So this is a pit design, but it's a cutback, so we have a very similar shaped pit that's just a bit smaller. And this is what we get. These areas, we have got very low incidences of issues. I can agree with that. Then you get green. So we've got, it's stable, but there are some local issues. Right? And again, you'll notice that slope is green. And yes, there is a structure set that's spaced quite far apart, and it does give us wedges once in a while. Now the big wedge that you get, lo and behold, there it sits. Right? We know as we mine those ones down, we tend to get wedges coming out there. So it does intuitively correlate with what we're getting. And then we've got the red areas where you've got the local instability. Now notice that the footwall, and the footwall is a lot flatter than the hanging wall. We know that the batters tend to fail, right? And that's been accounted for in the design. But the footwall looks pretty ugly, and it will. But we also know on the saprolites, we do get some issues there, usually when structures come through. So you've got to just be clear in the interpretation of this. I could probably, intuitively, I'll probably redo this and try and weight it so that I get a different color for that zone than that zone, because they're not quite the same. But having said that, I think that's a bit better than that. But at least this thing tells me that something's going on, right? And what I haven't done in detail, because I haven't been there thanks to COVID, is the worst bits of the footwall. Do they correlate where the TGM shear actually crosses the other shears? Which is, intuitively feels right, but I haven't had a chance to go have a look. So essentially, you've now got this risk imprinted on your pit shell. So this is a design-specific thing, or if you wanted to do it on actual, you can actually do it. And it's very simple. You export the pit shell to Gem4D. You can add your GSPI inputs to the pit shell, or if you don't want to use GSPI, you can use whatever else rating you want. And then you just use the if statement for the structure orientation components. It's a fairly simple one to work out. You calculate it in Excel, write to CSV, import it as a marker into Gem4D, and you color it on your pit shell. And then that's essentially what you get. Then you can export that colored pit shell as a CSV again. But in Gem4D, the risk rating will then be written as an additional column. So now you have a CSV file with X, Y, Z, and risk as an additional column. And if you bring it back into Gem4D as markers, you've got this ugly one. Each one of those fluffy little things represents an actual coordinate. And in this case, it's from 19 to 10, so as per the colors. Right. So the actual way to do it, so now you want to get to, you've risk assessed your pit shell, right? And you know where you're going to get issues. But you still want to put that onto your schedule. And that's actually quite simple. So what I've done here is you create a grid bounding box. Again, Gem4D function, and as Frans explained earlier, you've got this massive bounding box, but you don't want that for this. You only want grid points where you're actually going to mine. So what you do, you create the bounding box, you export it as a CSV, as a simple function, Then you import the CSV as a marker layer. Then you filter the markers only to be inside the pit shell. Right? And you've got the pit shell as a triangulation, so it's very simple. You filter it by downward movement. If it hits something, then it stays. If it doesn't hit something, then it goes. I didn't clear this up, but this is another pit next to it. I could have probably just trimmed that off, but for this purpose, it's okay. Then you export this grid marker data as a DXF, because you do want the DXF to be able to write your risk onto it, and then you bring it back in as a then you open the DXF file, and then you open your GSPI file as a CSV, and you write your CSV data for your risk onto your grid points as a DXF. There's a lot of importing and exporting in this process, but it sounds a lot worse than it actually is. It takes minutes. And then you color the grid by the GSPI, and then you export the grid as a CSV. And voila, now you've got a table. You've got a table of your risk versus your coordinates. And essentially, if you bring it back in, just to show you, so you'll have each point, and you've got the risk color-coded onto that. If you wanted to, you can look at horizontal sections, so let's call it bench plans. And yes, there are, because I've used Gem4D, and in this case I just use nearest neighbor, there's a lot of, if you wanted to be really or more precise, you could argue to yourself, well, I've got a green bit there and a blue bit there, but is it right? Did I color the green far enough? And nothing stops you from adding additional points if you wanted to make sure that you cover a certain part of the pit floor at the time with a new risk. You can do that if you wanted to. I didn't do it here, but you could. And finally, you end up with a table that is XYZ. You've got your dip and dip direction, but ultimately what you really want is your GSPI. And that's it. Now you get your mine schedule from the mine planners. I haven't done it in this case. As I said, this is hot off the press. Some of this was done last night. But you've got a database. Each block in your CSV represents a certain volume, right? And from your mine planners, you can very simply get a schedule that says, well, this block is going to be mined at this time. For underground, I know you've used the centroids of the stopes. One potential way that I worked out with our mine planners was, well, what if I use the end of month or end of period triangulations, and I can just filter these points by period? Again, just adding another column of when this will be mined is not difficult. It's something that you can fairly easily do. And then the last thing, because I didn't have a schedule, I just separated this by RL. And this is again from that database in Excel pivot table. Group it any way you like. I've grouped it by RL, so this is 2380 right at the top. That's 1980 at the bottom. And this is the percentage of tons to be mined, which I'm presenting here. You could do this by ore grade. You can pick it by any factor that you think is useful. And essentially, you're saying here that if you look at a range of scores 10 to 19, in the beginning we're going to have some 14s. Why so much risk in the beginning? Well, it's saprolites, right? We've had some historical issues. There's faults driven. You can get erosion. So we know the saprolites have a little bit of risk. Then you get to the end of the saprolites, and you start going into the greens, which is much lower scores. However, some of the slope will be on the footwall, and that's the bigger bit. And some parts of the footwall, and particularly the RLs where the structures intersect, you'll pick up some blobs of higher risk. So immediately you can plan things. Now in conclusion, as Kobus and Emrich said, so firstly you can assign a GSPI or any risk score to each mining block or mining time period, which is quite useful. And then you can optimize your schedule around mining risk. Now, I know this is something, and this is what we were really trying to get to. A couple of years ago, one of our mines in Brazil, they wanted to open a new open pit that's close to an underground working. And the initial risk assessment said, no, we can't do this. We just have to leave the pit because if it rains too much, there'll be some interaction. Right? But then we did a proper risk analysis. We worked out, we didn't quite do it this way, but we tied in the risk to each month and looking at the rainy season and risk and so on. And we worked out, well, actually, we can mine this pit, right? Because, but what the risk assessment told us is that we have 8 months, right? We have to do the whole thing in the rainy season, and the day the rainy season starts, we have to do the whole thing in the dry season, and the moment the rainy season starts, certain controls need to be in place to protect the underground workings. And we got that. We had a schedule. We knew, firstly, we can mine this, which is awesome news for the for the mine planners and for the managers. But the second thing is we've got a list of things to do. Right? There's certain things that we have to have in place at certain times, or mining stops. And we did that. We did mine it on schedule. We did have all the controls in place. And as luck would have it, we had a 1 in 50 year rainfall event almost the first week of the rainy season. And you know what? It didn't cost us any ore. Nobody got hurt. No equipment got damaged because we knew we had to be out of there in a certain time and with certain controls in place. And this is what we're aiming for with this whole process. Kobus's work, my work, is to take extra value that normally you would say, well, I can't mine this, probability of failure is too high. Well, let's understand where that risk sits. Where in time, where in space. And can we deal with it? Can we cut out blobs where the risk is actually acceptable as opposed to brushing probability of failure over the whole thing? And that just gives you so much extra power. Thanks very much.
Any questions for Julian? I think people are hungry there, Julian. Thank you again. And just quickly, Josephine from the ACG's here. They've got their ground support book. I know that a few young graduates have been bought it by their senior members, so just a hint for anyone out there that needs a copy. But yeah, lunch break. Thank you to the Anglo guys for presenting.
And that. There you go. Thanks. I have to apologize. I've got a meeting. But I didn't want to.
I need to put my presentation here.
This is the risk of fossil failure. Some of these things are actually I'm not a professional in terms of that field, but when I'm thinking about stuff, I'm technical about how things are. Let this do that. And I'm not saying that it's not present. I'm not saying that it's only well someone else doesn't have a full gambit of understanding. So they get what's
market data and then filter the markers and then check out the shelf, it's close enough and it saves me a lot.
different story. Let's go so much.
It's tricky. It's really so you've got and then you've got well, yes, so it's mining is in parallels. Where it's on grid, so like the whole is part of the hexagon grid. Like a geosystem.
Yeah, this way around. For you, no, that's the one.
What do you know But he doesn't have anything to do with line side data. So
Yeah, I've done it like
or the machine control side of things also comes from that. So, which at the time of the project, that is an insult, which is
Just find out what kind of money you're looking for. The other one, the other one is somebody right now.
sales oriented, not strategic.
Because then we can start trading straight up. It's the line and start. We have a lot of
Raising separate from
yeah. Where was your accounting paper? Is that Access?
I'm just going to have a look at that schedule and see how I can basically again most of the stuff. Yeah, I'll sign it tomorrow. We're getting on it now. Things like this, I'm going
Good to see you.
It's just very interesting work. Just